Okay, this is Intro to Taylor Polynomials. It's in between 10.1 and 10.2. It's just 2 pages, but I decided I was going to do this by itself. So we're just going to have this video, Intro to Taylor Polynomials. What we're going to be doing is, when we are talking about Taylor polynomials, we are talking about taking a function that is not easily differentiated, or it's not easy to calculate a value, and we're going to write it in terms of a polynomial. Now, sometimes the polynomial will look like the entire function if we kept going, like if we just would have to keep going, like an 8th degree, a 10th degree, we would have to have an nth degree, and it would be the exact same function. Sometimes it is only good for 1 point, and sometimes it's good for an interval of values where it would be exactly the same on that interval, or close enough that it, not exact, but sometimes exact, but close enough that it's very little error, okay? So basically what you're doing is you're taking a function and you're using calculus to make it be a polynomial function where the graphs look exactly the same for, like I said, either 1 point, for an interval of points, or for all points, okay, for all points. So those are your 3 choices. But what we're going to learn how to do here is just how to, what it looks like. So a Taylor polynomial exploration. Find the equation of the tangent line of y equals cosine x at x equals 0. Okay, so the first thing I would probably do is I would think about, well, if x is 0, what is my y? So cosine of 0 is 1. So I'm talking about this point, and I would also be thinking, what's my slope? So I would want to calculate my y prime is negative sine x. And then, of course, I would want to find my y prime at my x value in question, at this particular x value. So my y prime of 0 is going to be 0, because the sine of 0 is 0. So now I'm going to use my y equals m times x minus x1 plus y1. So y equals, here's my m, and I'll write this up here, m times x minus x1 plus y1. Okay, that's typically what we've been doing. So my m is 0 times x minus 0, and then plus 1. My y is 1. So this point is my x1, y1 point. Okay, and that's where the equation of the line is going to be. So if I simplify this, it's just y equals 1. So right here, the equation of my tangent line at x equals 0 for this function y equals the cosine of x, that's the equation of my tangent line. And so that's what we just did, sketch the linear approximation on the graph at the right. And that's what we did. Notice that our approximation has the same y value as and slope as the original function. What other property could be used so that it matches at the point x equals 0? And another property that I see that our function has is it's concave down. So I think that we could also use concavity as a property, because right now it's exactly the same at that 1 point, but it's not exactly the same anywhere else. So what if I kept going and looked at the second derivative so that I could look at, and try and involve concavity, like the second derivative tells me concavity. So what degree polynomial would this approximation need to be? And so for concavity, this would be second degree, right? So now what we're going to do is we're going to work on a quadratic approximation at x equals 0. So we've got our f of x quadratic approximation, and it's going to be a plus bx plus cx squared. and the function we're approximating is y equals the cosine of x. So if I take the first derivative here, I would get b plus 2cx. And that's just, the derivative of a as a constant would be 0, the derivative of bx would be b, and the derivative of cx squared, you'd bring the 2 down times c to the x. And then what about my y prime? Well, my y prime is negative sine x. And then I want to take that second derivative of my quadratic approximation. Since b is a constant, the derivative of b is 0, and since this is linear, I'm going to get the constant 2 times c. My second derivative here is going to be negative cosine x. So that's kind of what we're talking about, where if I want a quadratic approximation, I'm going to think of a quadratic function with a, b, and c, and I want it to look at least for 1 point, or maybe even a few more than 1 point, or a few more points. I want it to look exactly like y equals cosine x, centered at 0, at x equals 0, okay? What is the center of your approximation? X equals 0. Okay, that's the center of my approximation. Now they want us to find f of 0. So my f of 0 here is where my x is 0. Well, if my x is 0, I don't have a b or a c. All I have is an a, right? Because my zeros cancel out those two terms. And then my f prime of 0, if I put in 0 for x, it's going to cancel out that 2cx. All I'm left with is b. And then the second derivative at 0. Well, I don't have any x's, right? I'm supposed to put 0 in for x. I don't have any x's, so it's just going to be 2c. So be careful on that. That's easy to make a mistake and put it in for c, but we're putting it in for x. Now, what about the function we're approximating? Well, they want us to find y of 0. Wherever I'm centering it at, you want to find, your derivative and your function. So however many derivatives you need, and your function's values. So the cosine of 0 is 1. My y prime of 0 is going to be negative sine 0, which is going to be 0. My y double prime of 0 is going to be negative cosine of 0, which is negative 1. And it says, use the table above to find values for a, b, and c. So you can see that your a is 1, your b is 0, and your 2c needs to be set equal to negative 1. So my c is going to be negative 1/2. So let's do that again. I'll put it in a different color. My a is 1, my b is 0, and my c is negative 1/2. The quadratic approximation for cosine x. So if I want to do my quadratic approximation for cosine x, I'm going to basically take this and put in my a, b, and c. So my f of x is equal to, I've got 1 for a, my b is 0, so that whole term cancels out. And since my c is negative 1/2, this is going to be minus 1/2 x squared. So that is my quadratic approximation for the cosine of x. So if I come up here, and you could do it on your calculator also, you can sketch your 1 minus 1/2 x squared, and you can see that for, certain wider values of x, not just x equals 0, because x equals 0 was for the linear one, but now we've got the quadratic, and now it's kind of it's like spacing out. Oh, now it's good in between these x values. It's a very good approximation. And we could keep going, and the next one that we do, might be, well, I think I've already goofed here. The next one that we do might be a cubic function. And so it might look like this. And so it would be good for even more values, like let's say that many values, you know, so it's going to widen as we go, okay? And, you know, the next one would be a quartic function. And, you know, it would look more like, you know, a W or an M. And so as you go, it's going to get more exact and more exact for more x values, okay? So now it says, in the exploration, our polynomial approximation matched the value of cosine x, its first and second derivative, at the center x equals 0. Let's try to make that match more precise by using an even higher order approximation centered at 0. So we're going to do the same thing, only this time we're going to go to the 6th degree. And so the quadratic approximation for 6th degree is going to be f of x equals. So we've got our a, we've got our bx, we've got our cx squared, we've got our dx cubed, we got our ex to the 4th, we've got our fx to the 5th, and we've got our gx to the 6th. So that would be the quadratic approximation for f of x. The function we are approximating is y equals the cosine of x. And now, if we take the derivative of this 6th degree, we're taking the first derivative. The derivative of the constant a is 0. The derivative of the linear function is just the coefficient b. Derivative of the quadratic function, or quadratic term, I should say, should be 2cx plus 3dx squared plus 4ex to the 3rd plus 5fx to the 4th plus 6gx to the 5th. Sorry, I kind of ran in to our column here. And so this one, our y prime, is negative sine x. So now we're going to take that second derivative. Well, the derivative of b is 0. So this would be 2c plus 6dx plus 12ex squared plus 20f x to the 3rd plus 30gx to the 4th. Oh, and that's it. Sorry. It ran together, so I was running it together again. And then your y double prime here is negative cosine x. Now we find our third derivative. So 2c derivative is 0. 6dx is just going to be 6d. Plus, this is going to be 24ex plus 60fx squared plus 120gx to the 3rd. And our third derivative is going to be positive sine x. Our fourth derivative is going to be 24e plus 120fx plus 360gx squared. Our fourth derivative here is going to be cosine x. Our fifth derivative is going to be 120f plus 720gx. And our fifth derivative here is going to be negative sine x. Our sixth derivative is going to be 720g. Our sixth derivative here is negative cosine x. And so now we've got all that figured out. Now we're going to do it at the center, which is at x equals 0. So our f of 0, remember we're putting in 0 for x, so everything goes away except for a. Our f prime of 0. So for f prime, everything with an x goes away. I'm going to be left with b. Our f double prime, everything goes away except for 2c. F triple prime, everything goes away that has an x in it. I'm left with 6d. Fourth derivative at 0. Everything goes away with an x in it. I'm left with 24e. Fifth derivative at 0. Everything goes away except for 120f. And the sixth derivative at 0. There is no x. It's just 720g. The function we are approximating, they want us to find that at 0. So my cosine of 0 is 1. So over here, my negative sine of 0 is 0. My y double prime negative cosine of 0 is negative 1. My third derivative, sine of 0, is 0. My fourth derivative at 0, cosine of 0, is 1. My fifth derivative at 0, negative sine of 0, that's 0. And my sixth derivative at 0, negative cosine of 0, is negative 1. So now I can see that my a is 1. I can see that my b is 0. I can see that 2c is negative 1, so therefore c is negative 1/2. I can see that 6d equals 0. That means that d is 0. I can see that 24e is equal to 1. That means that e is 1/24. I can see that 120f equals 0. That tells me that f is 0. And 720g is equal to negative 1. That tells me that g is negative 1 over 720. And so getting it ready for that 6th-degree polynomial, it was a lot of work here. It says write the 6th-degree Taylor polynomial approximation of cosine centered at x equals 0, also known as a Maclaurin polynomial. So anything that's centered at 0 is called a Maclaurin. If it's centered somewhere else, it's a Taylor. I mean, it's almost like a square is a rectangle, but more specifically, it's a square. This is a Maclaurin polynomial, or a Taylor polynomial, or Maclaurin polynomial is a Taylor polynomial, but since it's centered at 0, it's more specifically a Maclaurin polynomial. So if you wanted to write there just to remind yourself, centered at 0. Centered at x equals 0. You know, wherever that point is on the function that you are approximating, okay? If it's Maclaurin, it's going to be centered at 0. It could be centered at 2, then it would be Taylor, you know, or 7, you know, wherever. So graph your result to see how close your approximation models the cosine of x. So since this is a Taylor polynomial, what we're doing is saying that the cosine of x is approximately equal to this 6th-degree Taylor polynomial. So that's what all of this says. So we are going to write our 6th-degree Taylor polynomial now. So our a is 1. And remember, you're using this top function right here to write it. And you're using all of these right here to put those values in. So the first thing I'm putting in is a equals 1. Your b is 0, so that one, it goes away. Your c is negative 1/2. So this is going to be negative 1/2 x squared. Your d is 0, so that goes away. Your e is 1/24. So this is going to be plus x to the 4th over 24. And then your f is 0, so that goes away. Your g is going to be negative 1 over 720. So this is going to be x to the 6th over 720. And then, of course, negative in front of that. So this is considered a 6th-degree polynomial, Maclaurin polynomial, that is equivalent to cosine for a certain values of x. And we will look to see what that is. But first, I want you to notice what this is equivalent to. So this is 1 minus. Now, this is x squared, and 2 happens to be 2 factorial, okay? Plus, this is going to be x to the 4th, and if I took 4 factorial, it'd be 4 times 3 times 2 times 1. It's going to give me 24. So I notice that 24 is 4 factorial minus x to the 6th, and this is 6 factorial. So you can write it like that to see the pattern. So that's why when they ask you, can you find p sub 8 of x, they don't want you to come up here and do another derivative or start all over. They want you to take and use this pattern to tell us what your next term would be. And you can see you're going every 2 and that the power is equivalent to the factorial. And so it's plus, minus, plus, minus. This one's going to be plus. This is going to be x to the 8th over 8 factorial. So there's your p sub 8 of x. That's your Taylor polynomial of degree 8 that is going to give you an approximation for cosine of x. And why is this important? Well, we can differentiate, integrate, approximate a polynomial much easier for a value near the center. So if I wanted to figure out what the cosine of 0.1 was, you know, I'm going to center it at 0 because that's very close. 0.1 is very close to 0. And so you center it at a integer value of x, and then you can use that Taylor polynomial to find x, you know, the solution to whatever your function is. This one is cosine. But we can do it, we're going to do it with all these other functions also. But you're going to be able to use that polynomial to approximate values close to that center, okay? And that is